Hello everyone, my name is Yuke Wang. I'm a fourth-year PhD candidate at the University of California at Santa Barbara. Today, I would like to introduce our work, QGTC, Accelerating Quantized Graph Neural Networks via GPU Tensor Core. Nowadays, graphs are everywhere in our daily life. For instance, in social network, we can use graph to model the user connection. In financial service, we can use graphs to model the transaction between different entities. And in molecular chemistry, we can use graph to model the interaction among different molecules. As a new and powerful tool to analyze the graph information effectively, graph neural network GNNs raise a lot of interest from the research and industry field. For example, in social network, we can use graph neural network to friend recommendation. And in financial service, we can use graph neural network for fraud detection. In molecular chemistry, we can use graph for molecular property prediction and classification. Next, we will see how graph neural networks operates under the hood. Let's start with the background introduction. In the first diagram, we show the basic computation flow of graph neural networks. Like the deep neural networks, graph neural networks also organized by layers that are linearly stacked together. But the operation is changed from those dense linear algebra, like the convolution layer and the dense gem operation, to sparse linear algebra, like the scatter and gather. Each graph neural network layer consists of an aggregation and node update operation, where the aggregation operation follows the graph-like operation, such as the PageRank algorithm, where at each iteration, we get the information from the neighbors for each node. While at the node update step, each node will update its information itself by using the information they collected from their neighbors. We also have several observations of the graph neural network that indicates its potential for quantized execution. First, the adjacent matrix of graph neural networks is naturally well suited for quantization, because when we can use the 0 and 1 to indicate the existence of an edge connection between different nodes. That is enough for maintaining the original information of the graph structure. And second, the quantization of the weight matrix and the node embedding matrix would also be benefits, because the precision loss in the quantization can largely be offset through the iterative neighbor aggregation. Meanwhile, this will increase the robustness of the graph neural networks when encounter adversarial attacks and input perturbation. On the other side, recent hardware advancement of the GPU hardware and programming toolsets are trying to leverage the powerful new hardware features like the Tensor Core for deep learning acceleration. Specifically, Tensor Core supports the basic computation primitive of a dense matrix multiplication, and where the matrix tell A and B are certain precision, like the 1-bit, 4-bit, or 8-bit, and the output matrix C and D use the FP32 or INT32. On the right-hand side, we also demonstrate the layout of tensor cores in the modern GPU stream processor subcore. For programming of the tensor cores, there are several approaches. The first approach is to leverage the cuBLAS APIs. However, leveraging the cuBLAS API, we can only have a limited option for the precision, such as the INT8, FP16. And another way is to use the web-level matrix multiplication accumulation primitive. This is the API from the CUDA-C. And on the right-hand side, we also demonstrate several basic operations provided by WMMA APIs, where the first one is to define a fragment for a matrix tile. The second API is to load the fragments by using the global memory or the shared memory to the registers. And the MMA sync is just to conduct the operation like the matrix multiplication on the loaded fragments. And finally, we store those fragments which are in the register to the global memory. However, directly collecting the quantized graph neural network with the existing GPU tensor core are facing several challenges. The first challenge is the current tensor core can only support a limited choice of the bit width, like the 1-bit or 4-bit. This is unable to meet the demands of users for any bit width precision computation. The second point is tensor core initially tailored for the dense gene computation that may not be directly fit the context of the sparse gene computation. This would cause the huge waste of the computation and memory access on those non-existent edges. And finally, the low-bit computation could cause the compatibility issue because we are unable to integrate the existing deep learning frameworks that operates on the well-defined data type like the FP32 with this low-bit data type. To this end, we introduced our design QGTC, which encompassing several techniques, as shown in this figure. Specifically, at the input level, we leverage metas for generating the dense small subgraphs from the large sparse graph. At the algorithm level, we leverage 1-bit based quantized computation for arbitrary bit width quantized gene computation. At the kernel level, we introduced our 1-bit adjacent matrix and 3D stack bit compression, zero-tile skipping, and the non-zero-tile reuse. And finally, we integrate our design with the PyTorch framework. In this slide, we will introduce more detail of our 1-bit based quantized computation. Let's start with the basic scalar-galar multiplication with one 3-bit number A and one 2-bit number B. We will first decompose the value of A and B into a set of factors in 1-bit representation. So when we multiply A and B, we will conduct a cross product of those decomposed factors and finally do the accumulation to get the exact output results. On the right hand side, we generalize such 1-bit based scalar-galar multiplication to 1-bit based vector-vector multiplication, where we will still apply the same process of the scalar and scalar 1-bit multiplication and cross elements accumulation to get the final output results. The thing here is that in the vector-vector multiplication of those quantized numbers, we can leverage efficient bit level and operation plus the population count primitives. Those can find its direct mapping on the tensor core, which can leverage by us to calculate the quantized vector-vector multiplication. Based on our 1-bit based vector-vector multiplication design, we introduced our 1-bit based quantized matrix-matrix multiplication, which will be used for our quantized gene computation. It consists of several steps. At the first step, we will decompose the bits from the input numbers. This including the decomposition of the adjacent matrix, decompose it from the FP32 to the 1-bit. And for the embedding matrix, we will decompose it to a number of the bits that are selected by our end users. And the second step is neighbor embedding aggregation, where we'll multiply the 1-bit adjacent matrix with the multiple bit node embedding matrix to get an updated node embedding matrix. And the third step is to neighbor embedding updates. Here, we will apply the weight matrix multiplication with the updated node embedding matrix after the neighbor aggregation. To facilitate our efficient implementation on GPU with the Tensor Core support, we carry out several kernel-level optimizations. The first one is called the 3D stacked bit compression. This is to help for our design to achieve the efficient memory storage. Specifically, it will pack the bit data into an int32 bit based on its bit position. And the figure below shows the case where 3 bits input embedding matrix are decomposed into 3 different 1-bit input matrix, where the elements from the 1-bit input matrix will be stored continuously. And the 3 bits, 3 1-bit input matrix will stack together. And each element of the 1-bit matrix is packed along either the row major or the column major dimension, depending on whether it appears in the left or the right-hand side operand, which will facilitate efficient computation for the later on calculation, just to avoid additional overhead from the data format transformation. Another kernel design is our zero-tile jumping technique, where we can explore the existence of non-zero elements inside a matrix tile to determine whether we need to carry out the matrix multiplication on those tiles. We also incorporate a non-zero tile reuse design, which will prioritize the final results generation of a small output tile by using those already loaded 1-bit adjacent matrix tile. Since when we prioritize the traversing of all tiles from the same bit matrix, we have to load the 1-bit adjacent matrix tile from different tile positions many times. However, in our method, we only need to load such 1-bit adjacent matrix tile once. In addition, we also introduced our PyTorch integration, which will further improve our design portability and programmability. Specifically, we introduced a novel type called the bit tensor data type. Specifically, we will use the 32-bit integer tensor in PyTorch as the major vehicle for holding any bitwise quantized numbers. And we also introduced 2 APIs. The first one is tensor2bit, which will encode the int32 or 14.32 numbers into a bit tensor. And the second API to value is to decode a bit tensor as the int32 or 14.32 regular tensor. In addition to the bit tensor data type, we also have a bit tensor computation. There are 2 APIs. The first API is bit matrix multiplication to bit, which we will take a 2 low-bit tensor as an input and generate another low-bit tensor as an output. And the second API is bit multiplication to int, which will take 2 low-bit tensor as an input and generate a regular tensor like the int32 or 14.32 tensor as the output. In our evaluation, we cover different GNN models, including the cluster GCN models, which is popularly used in many GNN algorithm work. And we also cover the batch GNN model for comparison. For baselines, we cover the deep graph library as our major baseline for end-to-end evaluation. And for kernel-level performance, we also cover the cuBLAS library as well as the open-source qtLAS library. For platform, we choose a desktop server with 8-core 16-thread Intel Xeon CPU with 64 GB host memory. And our GPU device is the NVIDIA Ampere RTX 3090 with 24 GB device memory. For dataset, we cover 3 different types of dataset with different vertex, ages, as well as the dimension and output classes. In terms of the end-to-end performance, our design was compared with the deep graph library on cluster GCN and the batched GIN. For instance, compared with the cluster GCN on DGL, our design could achieve the 2.6 speedup on average across different number of bit choice. And compared with the DGL on batched GIN, our design could achieve an even higher speedup, the 2.8 times speedup across different bit choice. In addition, we also compare our design with the cuBLAS gene int8 precision on Tensor core. This is the lowest available choice for cuBLAS gene, and we compare our design in terms of the throughput with respect to the cuBLAS baseline. And we can see from the sub-figure C, our design can outperform the cuBLAS int8 on all settings with different number of bits. For additional studies, we also compare against the latest Quantized library with the int4 precision on the Tensor core computation. In terms of the throughput from the table 3, we can notice that our design can achieve evident higher throughput compared with the Quantized int4 with different number of the bit choices. And we also measure the effectiveness of our zero-tile jumping technique. As we can see from the right-hand side figure, our zero-tile jumping technology can effectively reduce the number of the tiles up to 70%, which can effectively reduce the tiles when we conduct the computation on those highly sparse input adjacent matrix. Additional study also covers the adjacent matrix size impact on our design's performance. As we can see from the left-hand side figure, with the increasing size of the adjacent matrix, our design can scale well with the increase of the GPU throughput. And such increase will gradually approach to the upper bound of the GPU Tensor core computation throughput. Further, our non-zero tile reuse can improve the throughput performance on those large matrix size, because under those settings, with a higher number of bits, we can save a more unnecessary data loading for the adjacent matrix tile, because we can reuse it for more times. Thank you for listening. That's all of our talk. And if you are interested in our project, feel free to reach us by email or to check our code at GitHub.